Hello and welcome to week 12, lecture 2 of CO 442642 graph theory. Today we'll be discussing flow-coloring duality. So we'll be talking about flows to remind you again of some important theorems from last lecture. Tutte in 1954 had shown that a graph has an H-flow, that's a group flow for the group H, if and only if it has an H-prime flow for all groups of order H. So if you have one for any group of that order, you have one for all of them. So that showed that for groups, it only depends on the order of the group and not on the structure of the group itself. Again, for finite abelian groups. Then Tutte actually earlier in 1950 had shown though that a graph G has a ZK flow if and only if it has a K flow. So these integer flows are related to actually cyclic group flows and therefore to other groups of that order. Now an important note that maybe we didn't make hay of last time is that a graph has a K flow. If it has a K flow, then it has a K prime flow for all K prime greater than or equal to K. Because what's the requirement? We need to satisfy Kirchhoffs Law that you're actually zero at every vertex, and then you only use the values kind of 1 up to K minus 1, or their negatives. So of course, if you do that, then allowing one to just add more higher values, then you'd have a K prime flow. So a K flow is a K prime flow for all larger K prime. So that really tells us that we can actually define what's called the flow number of a graph G, denoted phi of G here as the minimum K such that G has a K flow. So analogous a bit to chromatic number and such, but here about flows. So that's quite nice. And so today we'll be kind of talking through the values for various graphs. What are the flow numbers of various graphs? When can we get the various flows, especially for small numbers, as you'll see why in a bit. But I want to make one important note is that if a graph has a bridge, then it emits no flows. So remember a bridge, an edge that would create two components when you delete it, then if you have a bridge, you have no flow. Why is that? Because if you had flow, then what happens, the flow member across a cut has to be 0. And that would mean that that edge would get a value of 0, and it wouldn't be nowhere 0. So it wouldn't be a flow as per our definitions. So we'll really be only studying bridgeless graphs, graphs without bridges. All right, so let me go through some small flow values. So let's start with 2 flows. A graph has a 2 flow if and only if all its degrees are even. This is the claim, a theorem. So how do we prove this? Well, the point is by Tutte, by that theorem, a graph has a 2 flow if and only if it has a Z2 flow. And what is a Z2 flow? Well, you're allowed the value 0 or 1, but you're not allowed 0 because it's nowhere 0, so really you're only allowed the value 1. So therefore, a vertex satisfies Kirchhoffs Law for a Z2 flow if and only if it has even degree. For example, look at this picture, right? If they're only allowed a value of 1 and I don't care about direction because 1 is equal to -1 mod 2, then you would see that really if I have even degree, I'll satisfy Kirchhoffs, and if I have odd degree, I don't. So it's if and only if they're even degrees. So that's 2 flows. So 2 flows are really just equivalent to these even subgraphs, which are kind of like Eulerian circuits, but you're allowed to, of course, have different components of even degrees. So that's the 2 flows. What about 3 flows? They're more complicated, but a nice theorem is that a cubic graph has a 3 flow if and only if it is bipartite. So here let's just study cubic graphs, which is nice. So let's prove this theorem. So a degree 3 vertex satisfies Kirchhoffs law for a Z3 flow if and only if all its incident edges have the same value. So you can study the picture here, right? So if I have 3 edges, I have values 1 or 2. Let's just orient them all toward the vertex, say, because otherwise it just will flip to its inverse. So if they're all incoming 1, that will be 0 mod 3. So that will be fine. But if it's 2, 2, 2, 1, 1 or 2, 2, 1, that's 4 or 5. So that's 1 or 2 mod 3. That's not acceptable. And 2, 2, 2, that is indeed 0 mod 3 as well. So that is acceptable. So that's the nice part about cubic graphs with Z3 flows. They all have to have the same value. Also, there are only 2 such non-zero values, 1 and 2. So then there's only really 2 options. And hence, if you're a cubic graph and you have a Z3 flow, you're naturally bipartite. So you can actually make this bipartition, where the ones that with incoming 1s go on one side and the ones with incoming 2s go on the other. You could actually show, therefore, it's actually a balanced bipartite graph with equal sizes on both sides if you count up the numbers, but that's quite nice, right? So we have this for cubic graph. If you're a cubic graph, then you are bipartite, and conversely, if you're bipartite, what do? We direct the edges from A to B with value 1. So we kind of just invert that procedure. We just direct from one side to the other and give them all the same value, and then they'll satisfy Kirchhoffs Law as above. So those are two small proofs. I wanted to do a couple more today. So we'll talk about 4 flows. So there's a nice theorem of Jaget from 79 that says that every 4-edge connected graph has a 4 flow. And again, really by Tutte, it suffices to construct a Z2 cross Z2 flow. So this is the really nice part, and it shows up a lot in these theorems, is instead of proving a 4 flow or 3 flow exists, we look to these group flows. So that's really the power of Tutte's theorems from before. So we now know, it suffices to construct a Z4 flow, but really by Tutte again, it's a Z2 cross Z2 flow because it doesn't matter what group we use, and it'll be nice. So how do we do this? Well, since G is 4-edge connected, let G be this graph we're doing, then by a theorem of Nash-Williams, there exist 2 edge disjoint spanning trees T1 and T2 of G. So we don't really talk about that, but it is in D still, that if you're a 2K edge connected graph, you have K edge disjoint spanning trees. So if you're 4-edge connected, there are 2 edge disjoint spanning trees. So now we're going to use that to our advantage to build the flow. How does this work? Well, for every edge that's not in the first spanning tree, E of T1, will flow a value of 1, 0 on its fundamental cycle CET1. So remember, every edge not in a spanning tree has a fundamental cycle with that spanning tree. And so now we get this fundamental cycle, we'll flow it. It doesn't really matter the direction, pick a direction and put a flow in the first coordinate in that direction. And now what happens? Well, everything outside will have non-zero coordinates in the first value, everything outside of T1. So the issue is the edges that actually have 0 at this point. So let F be those edges. These are edges in T1, we'll call them E prime, where if you sum all the fundamental cycles that are on, all the flows, somehow, unfortunately, it doesn't add up to 0. So it would be kind of in an even number of those cycles. So now what do we do if you happen to have edges in an even number of fundamental cycles for T1? Then what we do is we'll use T2 to repair the flow. So how does this work? Well, for every E prime in F, we'll flow a value of 0, 1, and that's 1 in the other coordinate on its fundamental cycle CE prime T2. So we do that, that will end up ensuring that it indeed, with the second coordinate, has a non-zero value, and then we'll be fine because everything in T2 already was given a 1 in its first coordinate. So you won't end up 0 anywhere, and this will indeed be a flow. So that's the proof that every 4-edge connected graph has a 4 flow by Jaget from 79. One other thing I wanted to say about 4 flows. So a graph has a 4 flow if and only if it is the union of 2 even subgraphs. So if you think about that more, again, you have a 4 flow if and only if you have a Z4 flow, if and only if you have a Z2 cross Z2 flow. And a Z2 flow is really just, it means you have an even subgraph with that. So really you could divide into these 2 even subgraphs and vice versa. So that's the nice part about 4 flows. And the proof is just what I mentioned because of the Z2 cross Z2 flow nature. Another theorem that's nice is that a cubic graph has a 4 flow if and only if it's 3-edge colorable. So if you look at cubic graphs, turns out that their 4 flows are nice, namely it's for 3-edge colorability. So what's the proof of that? Well, again, a degree 3 vertex satisfies Kirchhoffs law for a Z2 cross Z2 flow if and only if its incident edges have different values. So you can think about that, again, think about 3 edges coming in. What would it mean? Well, so in the first coordinate, you have to be even. So there'd have to be 2 values, it turns out, that are 1, and the same in the second coordinate. And since they're not allowed to be 0 anywhere, they have to all be different. So namely, you'd have to have C1, 0, 0, 1, and 1, 1 at each of the 3 different edges. And this is if and only if. So you can think through that. But what that means is that those are the 3 colors you should use. So if you had this flow, you could just let 1, 0 be a color, 0, 1 be a color, and 1, 1 be a color, and this would create a 3-edge coloring. Vice versa, if you have a 3-edge coloring, just declare one of the colors to be 1, 0, one to be 0, 1, and another to be 1, 1, and that would give you a 4 flow. So that's quite nice. It'll come back around when we talk about which cubic graphs have 4 flows. Well, here we know the answer, but to more general conjectures. So that's all I wanted to say about small flows. I wanted to move on now to the promise of the title, Flow-Coloring Duality. So how are flows and colorings related? The key is planar graphs. So you might remember the definition of a planar dual. So let G be a plane graph. Then the dual of G, denoted by G star here, is the plane graph where the vertices of G star are the faces of G. The edges of G star are, say, F prime. If F and F prime, of course, would be faces then of G, where there exists some edge that's incident with both F and F prime. So if two faces border each other, we'll put an edge in G star there. And then it turns out then the faces of G star actually correspond to the vertices of G, and so if you took the dual again, you'd get the original graph back. So again, that's planar duality, and what the fundamental thing and the main theorem of today is, proved by Tutte in 1954, is that if G is a plane graph, then chi of G is actually equal to phi of G star. So the chromatic number of a plane graph is equal to the flow number of its dual. That colorings and flows are actually dual objects. So in this sense, flows become kind of their own fundamental thing. So colorings were quite fundamental. Colorings are very nice for planar graphs, and it turns out then those are dual to flows in planar graphs. And so maybe, as you'll see in a bit, if we have coloring theorems about planar graphs, those give rise to dual theorems about flows in planar graphs, and you might wonder, how do those generalize? What's true in general about the flows of graphs? But first, before we do that, let me prove this theorem of Tutte, establishing the flow-coloring duality. So to do that, I'll have to prove to you kind of both directions. So I'll prove that colorings give rise to flows, and that flows give rise to colorings. One small point I'd like to point out is, if you think about it a little bit, it suffices to prove this only for when connected graphs, when G is connected. Why is that? Well, what happens if you have components, then you kind of have like cut vertices as faces in the dual. And so what happens then, if we establish it kind of for the colorings, there'll be kind of flows of the different blocks of the graph. And then it turns out, you have a flow if and only if your blocks have flows. Similarly, you have a coloring if and only if your components have colorings. So let me just assume connected for the sake of example. And remember, all of this is applying really to multigraphs. So we didn't really get into that. I'm not really stating it, but I define flows that way. And what about coloring in multigraphs? Well, multiple edges don't make any difference to coloring, so you could just ignore them. The thing that does make a difference is loops. So if you have a loop in a graph, then you just have no coloring as possible whatsoever. Luckily, loops in a graph correspond to bridges in the dual, and so remember, graphs with bridges don't have flows. And so actually, this bridge-loop duality establishes that. So let me assume, say, you don't have any bridges in the dual or loops in the original for proving this theorem. So how do we get from colorings to flows? So this is quite nice. Let phi be a k-coloring of G. I'll need to show you a k-flow. So how do we do that? I'll define f on the dual, so this is on E of G star, by letting f of E star, so E star is some edge in the dual, by taking it to be phi of U minus phi of V, where U is the left end of the dual edge E as viewed from the direction of E star. So here's a picture to make that make more sense. So suppose kind of black is my original graph G, and I had an edge E equal UV in G, then that's dual to some edge E star, which goes from one face to another. So let's call them F1 and F2 here. So blue is my dual graph. And we had this coloring, phi of U, phi of V, then the point is, since it's planar, it's orientable, right? The plane is orientable, so I have a left side and a right side. So again, we're doing it for a direction of flow. So say I want the value in this direction, then I could take the left end, phi of U here, minus the right end, phi of V. And the claim is that then this is really our flow that we want. So let's go through the various properties. One thing to note is that f of e star, the absolute value is at most k minus 1, since phi of u and phi of v are between 1 and k. So that is quite nice. We're restricted to those values we need for a k flow. Another point is, as it's a coloring, u and v are never equal in color, so that means the f is nowhere 0. So we've established that we have the right values. It's nowhere 0. It obviously has this anti-symmetric property, because if you look at the other direction of E star, then V is on the left side, and so it'll be the negative of what it was in the other direction. So that all works. The question is, do we satisfy Kirchhoffs law? So I claim that we do satisfy Kirchhoffs law, and I ask you why. So you might want to pause the video and think about, why do we satisfy Kirchhoffs law? Maybe work out a little proof for yourself. Otherwise, I'll continue with the slide to show you in more detail that proof. But it intuitively makes a lot of sense. So how does this work? Well, let V be in V of G star, right? This is where we have to show Kirchhoffs works, i.e. therefore V is a face of G, right? It's a vertex in the dual, so it's a face of G. And then what you do is you consider the boundary walk. Let's label it W1, W2, Wm of V and G. And of course, that could be, vertices that you're seeing multiple times, but let's just ignore that again because we're thinking not about bridges. And then what we get is this picture, right? So you have this this face, W1 up to Wm, and what happens is, those edges of the boundary walk form, right, duals in the blue graph, right? So you get these dual in the blue graph, these dual edges, and we want to count the edges, the value of the flows coming out of there. So let's do this. We sum up the f of E stars. Again, think of them directed out of E from V. And what we find is, well, that first edge has W1 on the left as viewed from V. So it'd be phi of W1 minus phi of W2. The next one is phi of W2 minus phi of W3, and so on as you go around until you get a last edge where Wm is on the left, so it's phi of Wm minus phi of W1. And if you stare at that sum, the point is that everything will cancel out and you'll get 0, right? Because W1 will be once a right vertex and once a left vertex. And so everything will nicely cancel. And that establishes that Kirchhoffs law is satisfied. We had this anti-symmetry property on the directions, we had the right values, and we were nowhere 0. So indeed, F is now a K-flow as desired. So now what do? We want to go from flows to colorings. So let F be a K-flow of G star. I need to show you the coloring that corresponds to it. How does this work? Let V be a vertex of G and T be a spanning tree of G. So we have V being any vertex and T being a spanning tree. And here's I'm using connected. So now let me show you how to get the flow. Basically what you need to do is you need to pick a color for V. You think of V as the root, so I'll just color it 1. And once I've done that, I can now invert the previous procedure to define a color for each vertex in G. So the key idea is that if the flows tell you the differences of the colors, then really I could take that idea and define colors for the vertices, but I need somewhere to start to anchor kind of the coloring. So that's where V will play. The role of the root will just define V arbitrarily to be 1, and then from there, using T, we can go ahead and define the color at every other vertex. So here's a picture kind of that. It's not complete, but just showing kind of locally what happens. So, if V was colored 1, then I have, say, flow on the dual edges, right? So black is the original graph G, and the blue, say, is our G star. Then what happens is, so, say I want to go from V up to that top left vertex. Well, if the flow is 1 there, then if I want to make it consistent with the previous procedure, then I want 1 to be equal to the difference of the left color minus the right color. And the right color is 1, it's V. So the answer is that the top left vertex has to be colored 2 to make that consistent. Similarly, 3 has to be, 2 plus 1. So that top right vertex indeed has to be 3. And this is how I made the green numbers. The colors, I worked out from the various flows what the color should be. And you continue along this. So if you're not a neighbor of V, now you've colored the neighbors of V, then you establish the colors of their neighbors, and so on by the spanning tree. So namely, as I just said, you use the values of the f of e star. Important note though, you're only using it for the edges in the tree. So to be well defined, I'm only going to use it currently for the edges in the tree to actually decide what the color is. Now it'll turn out that that actually is well defined. So if you stare at this picture and look at the edge between 2 and 3, if you look at the flows around that vertex, you would see it'd have to have 1 coming in, which would actually work with the value. And that will establish that it's indeed a coloring, but that's what we need to do. So let me just do it more formally. So I claim that phi is a coloring. So namely that for every edge, phi of x is not equal to phi of y. So this is edges in that black graph, that original graph. And well, if e is an e of t, this is just immediate from the definitions because f is nowhere 0. What about if e xy is not an e of t? Consider the fundamental cycle c of e. So if you go back to that previous picture and took an edge that's not in the tree, it would have this fundamental cycle. And then what happens is that corresponds to a cut, right? So a cycle, this c of e, will be a cut in the dual graph. It'll cut the inside and the outside faces from each other. And so what you can do is you know that the flows across the cut must be net to 0. And you can work out then, well, that's the flow of E star plus the sum of all the other edges from the fundamental cycle. Those ones actually were used to define the coloring. So if you work through those and you cancel along that path, it turns out to be phi of x minus phi of y if I take the directions correctly. And the important point then is, since f of E star is non-zero, because we're nowhere 0 flow, phi of x is not equal to phi of y, which completes the proof that it's a coloring. So really, if you just think about this in a little more detail, it's really saying actually that f of E star would be that correct difference. That for every edge, not even the ones in the spanning tree, this cycle cut duality and the fact that cuts have net flow 0 means that the flow rule will also be valid for them, that it would be equal to the difference if you do it in the right direction. So that establishes how to get from colorings to flows and flows to colorings. So from colorings to flows, you just take kind of the left-right difference, and that will work out to be the flow you want. For flows, you kind of just invert that procedure. The thing is, you actually have to pick at least one color somewhere, and then spread that color around, at least in a connected graph, to then force the coloring everywhere. And then that will work. It will be consistent. So that establishes Tutte's theorem. Now I wanted to get back to just a little wrap-up of what does this mean for general graphs. Well, I should remind you about coloring theorems for planar graphs. So the 4-color theorem says, every planar graph has a loopless planar graph, has a 4-coloring. That means that every planar graph has a 4-flow. And that should have, of course, say bridgeless there as to be loopless. So sorry about that for the typo. So that's the dual of the 4-color theorem. Similarly, and again, this should also, well, it should say bridgeless, but actually it's implied by 4 edge connected. So turns out the dual of Greuch's theorem is every planar 4-edge connected graph has a 3-flow. Why is that? Well, what does Greuch's theorem say? It says that you're triangle free. And it turns out triangle free, the dual of that is having no 3-edge cut. So if you're triangle free, then you have no 3-edge cut. So really a kind of dual formulation of Greuch's theorem is every planar 4-edge connected graph has a 3-flow. So that's quite nice, right? Because Jaget, we knew every 4-edge connected graph had a 4-flow, but if you impose planarity, you can get that down to 3. And the question is, could these flow theorems hold for general graphs? So that's really stark, right? Coloring, you just can't expect that, right? Complete graphs, the chromatic number gets larger and larger. We didn't show, but it's indeed still, the complete graphs only do admit 3 flows always. So they're not kind of counter examples. So you might begin to wonder, well, maybe just every graph has a 4-flow, or every 4-edge connected graph has a 3-flow, etc. Maybe planarity is no longer important. And indeed, maybe it's that somehow the planar coloring theorems are true because their flow versions are true, that they're dual to these more general flow questions. There is one thing, not every graph can have a 4-flow because of the Peterson graph. So it turns out the Peterson graph, it's cubic, but it's not 3-edge colorable. And so it doesn't have a 4-flow by what we've established. However, it's not that hard to find out that it does have a 5 flow. So I won't show that to you, but it does make us have to tweak the conjectures a little bit. So indeed, Tutte, amazingly, when doing all this work on flows, made the following very general conjectures. So one is known as the 5-flow conjecture, that every bridgeless graph has a 5 flow, that 5 is the right number in general. So somehow Peterson's the obstruction there, and really we can get kind of 5 in general. So that's quite nice. He made another one, that was in 54, he made another one in 66, the so-called 4-flow conjecture, really asserting that Peterson's the main problem, that every bridgeless Peterson minor free graph has a 4-flow. So that would be quite nice. That isn't quite perfect in that minors don't necessarily preserve flow number, but would be a nice fact to be true, kind of the best we could maybe hope for about 4 flows. And then the 3-flow conjecture is quite startling as well. It says that every bridgeless 4-edge connected graph has a 3-flow. So again, I don't need bridgeless there since we'd be 4-edge connected, but saying that every 4-edge connected graph has a 3-flow. So generalizing Greuch's theorem kind of from planarity, at least in this flow version. And that would improve upon Jaget's value. So what is known, so let me just wrap up by telling you what's known about each of these conjectures. For the 5-flow conjecture, every bridgeless graph has a 5-flow. That was not proved, it's still open, all of these are open, but Jaget in 79 showed that every bridgeless graph has an 8-flow. So how does this work? The proof constructs a Z2 cross Z2 cross Z2 flow. So it's something like you want to use kind of different spanning trees that cover the whole graph in a way to establish that you actually have this flow. So it's similar in spirit to the 4-edge connected 4-flow one I showed you before, but I'm not going to do that. Another one that is quite nice is Seymour in 81 improved on this to show that every bridgeless graph has a 6-flow. So you can go ahead and read that proof in Diestel. It's quite nice. And the idea is to construct a Z2 cross Z3 flow. So that's somehow the nice things about 8 and 6 is that they're not prime, so you can actually look to other groups than just the cyclic group. Whereas the 5 flow seems quite hard to get the Z5 flow in general. So that's the state of the art of the 5 flow, and there's been no progress, and I mean there's not really room for incremental progress. We're at 6 and we need to get to 5. What about the 4 flow? Well, so again, by Tutte in 66, well, it should be pointed out for planar graphs, which don't have Peterson as minor, having a 4 flow is equivalent to having a 4 coloring. So this is really equivalent for planar graphs to the 4 color theorem, which at the time was just a conjecture. So it was maybe hoped that flows would be a way to prove it, but eventually was given the discharging proof by Oppel and Hawken, and so established for that. What else is known? Well, Robertson, Sanders, Seymour, and Thomas in 98, announced in 98, and I think still being kind of published to this day, prove that it's true for cubic graphs. So that's quite nice. Why is that nice? Well, even for cubic graphs, it generalizes the 4-color theorem. Why? Because it suffices to prove the 4-color theorem for triangulations, which are really cubic graphs, dual to cubic graphs. So it turns out the 4-color theorem is equivalent to proving every cubic graph has a 4-flow or equivalently a 3-edge coloring, and this is really generalizing it to say every cubic Peterson minor free graph, bridgeless there, has a 3-edge coloring. So quite nice. But that's a long series of papers and also relies on kind of proving the 4-color theorem or reproving it with even more discharging. So then let me wrap up with talking about the 3-flow conjecture. So from 72, every 4-edge connected graph has a 3-flow. I'll point out that Jaget in the early 90s showed that it's equivalent to prove it for 5-edge connected graphs. And Thomason in 2012 had a big breakthrough where he showed that every 8-edge connected bridgeless graph has a 3-flow. Again, don't need bridgeless there. And this was improved by Lovaas, Thomason, Wu, and Zhang to every 6-edge connected graph has a 3-flow, which is quite nice. So that was quite an amazing result. Thomason and then with other co-authors, because at that point it wasn't known whether any value worked, whether a million edge connected had a 3-flow, and it turns out that not only 8 did, and then they improved it to 6, which again leaves us just one step short, as 5 would be enough. Alrighty, so that concludes what we talked about for flows, and actually this being our last lecture, that's really the end of the class. So I just wanted to summarize what we covered in the class. We did a lot on coloring, so we did Brooks' theorem, Vissing's theorem, Thomason's 5 list coloring theorem, and various extensions of those. We moved on to minors. We learned about surfaces, we learned about tree width and grids, brambles, the graph-minor structure theorem, Hadwiger's, etc. Then we moved on to extremal graph theory, where we learned Turan's theorem, we studied the regularity lemma, the Erdos-Stone theorem, the blow-up lemma. We did some Ramsey theory, and particularly Ramsey's theorem, and the bounded degree theorem for Ramsey numbers, and talked more about them. And we did the probabilistic lower bound due to Erdos. And finally, we wrapped up with flows, where we studied flow-coloring duality and the group flows, and talked about Tutte's flow conjectures. So all in all, we covered a good bit of D-Still and a good bit of graph theory all around all these different flavors. So that concludes this graph theory class. Until next class or next time, see you then.